Welcome back. So this video will cover the high-level concepts for how we will implement precise state. And we'll start with a hardware structure called a reorder buffer, but first a quick motivating example. We have 4 instructions here, a segment of a program. We'll assume all of the registers are 0, R2, etc. are ready. I1 can start its execution right away, but there's a read after write dependence on R4. So I2 must wait until that version of R4 is available. But meanwhile, with out-of-order execution, it's likely that instructions 3 and 4 will compute their results before the long latency and data-dependent multiplies of instructions 1 and 2. Because their register inputs, their operands, we'll assume that they're ready in the register file. So there's no dependence here. These are independent instructions in our instruction window. Given the write after read and the write after write hazards in this instruction stream, we need to make sure that the results are stored back to the architectural registers in program order, both to eliminate write after read and write after write hazards and to implement precise state. The reorder buffer is a crucial structure toward this goal. Now, conceptually, the ROB is a FIFO queue containing a flag indicating if an instruction has completed its execution, and it contains both the new and old register mapping of the output register for every instruction. So how does it conceptually fit into our pipeline? Well, we've augmented the diagram from the last video to implement the instruction buffer or instruction window with the reorder buffer. Conceptually, this structure, the ROB, it buffers completed results, so output register values, that are en route to the register file. This structure is responsible for ensuring we make in-order write-back to the register file. And just as we split the decode stage into an in-order part and an out-of-order part, we do the same here, splitting the write-back stage into 2 parts. We call them complete, the complete stage, and the retire stage. So that's W1 above and W2 above. So the high-level operation here is that dispatch still sends instructions in order to the instruction buffer, the reorder buffer, which then issues the instructions out of order when their operands are ready down to the functional units. But instead of writing back the results directly to the register file, the complete stage instead buffers the output register value in the reorder buffer, holding instructions and their output values in order, while the second write-back stage, the retire stage, writes back the registers in order. So let's see these in action. The complete and retire stages. During the complete stage, instructions that have completed their execution, they will write their result into what's called a physical register file. I'll cover that in more detail shortly. And recall that the reorder buffer retains both the new location of the output register as well as the old to enable abort and restart. So this stage is out of order. Instructions wait in the reorder buffer, which holds both the new and old register renaming mappings. And because they wait in the reorder buffer, this doesn't backpropagate to younger instructions. Just like how waiting in the reservation station doesn't backpropagate any delay in execution to younger instructions. In the retire stage, which is also known as commit or graduating, the reorder buffer returns the old physical register for the output register name to a free list. So we've now given up the ability to abort and restart. We've committed the state of a register to the value in its new location, in its new physical register. And this process, crucially, happens in order so that we can always recover the precise state at every instruction. All of the instructions younger than the one that's currently retiring, we still have entries for them in the ROB and therefore have the ability to abort them, to recover. Now, because this retire process is in order, a stall can backpropagate to younger instructions. Say if a younger instruction is in the dispatch stage, so it's trying to allocate a reorder buffer entry. If the ROB is full, because we have not retired enough instructions quickly enough, then this stall backpropagates to that dispatching instruction. So conceptually, the reorder buffer gives us the data and the means to recover in case of control misspeculation or a precise interrupt. We can recover the precise state at every instruction in terms of registers. But what about memory? That's another crucial part of the ISA. That is other state in the machine. So that brings us to the concept of a load store queue. The ROB makes register writes in order, but what about store instructions to memory? Well, what if we did them as usual? So we issue stores straight to the data cache in the execute stage. Is that a viable option here? Well, no. Imprecise memory is arguably even worse than imprecise registers. So the load store queue is another hardware structure that comes to the rescue. Completed stores who have computed their effective address will write to the load store queue, to some entry in the load store queue, only when a store retires is it written to memory. Specifically, if a store is retiring, then it must be at the head of the load store queue, another FIFO queue. So the head entry of the load store queue is written to the data cache or memory. So those two steps cover how a load store queue acts as a sort of functional unit for store instructions. But what about load instructions? Now, if a store writes to some address A and a younger load reads that same address A, of course the load must return the value written by the store. That is, this load and store that share the same address have a read after write dependence that must be respected. So when a load executes, that is, its effective address is known, it accesses both the load store queue and the data cache in parallel. The idea here is to avoid stalling loads until their predecessor stores have retired. That could take a long time. So the big idea is to forward the value for the load from the load store queue if an older store has a matching address. In other words, if there is a read after write dependence. Now, these load store queues have a lot of design options that I can't cover in detail in the lectures. The textbook covers several of the design options, including conservative versus optimistic scheduling of loads and stores. But I'll emphasize that crucial requirement. A load that reads address A must return the value written by the youngest previous store that also wrote address A. So this means that if the address of any stores that precede some load are unknown, the younger load instruction must either stall or speculate. This is a dependence on memory operations. So I refer you to the textbook for more details about these options. But I'll give a high-level overview of the reorder buffer and load store queue in action to enable out-of-order execution of our instruction stream while retaining precise state so that we can recover from misspeculations or exceptions and interrupts. The basic idea is that load store queue entries are allocated in program order. It is a FIFO queue. When a store issues from the abstract instruction buffer or reorder buffer, we'll see soon that there are reservation stations under the hood there. The store data and store address are written to the load store queue entry for that store. The head of the load store queue finally writes to the data cache when that store instruction is about to retire, so that if we need to recover precise memory state, we simply flush the load store queue. Only the data that should be in memory is in memory. Meanwhile, load instructions check the load store queue to find the youngest older store that has a matching address to the load's effective address. And if one is found, say in this entry here, we send that data to the load. It represents the most recent store value. Otherwise, we take the value from the cache because it must be that the last writer to this address has already retired. I will wrap up this video at this point. We've covered the key concepts where the reorder buffer will hold both the new and the old register mapping for every instruction so that we have the data to recover back to precise state. And since chip resources are limited, the reorder buffer retires its instructions in program order, again, to ensure that we can retain state. And the load store queue exists to make memory writes in order while respecting read after write dependencies on memory accesses to the same address. I'll see you in the next video where we will cover the MIPS R10K architecture, one possible implementation of this out-of-order execution with reorder buffer design. I'll see you there. Welcome back.